Greetings, young humans. I join you for your celebration of All Hallows Eve. And for that celebration, I bring you both a trick and a treat. The trick is knowing that you have an exam in your near future. The treat is helping you prepare for the exam by completing this worksheet with you. If you can complete the worksheet by yourself, you shall have success on this exam. So I bring you pumpkin physics. Oh. Okay, guys. Thanks for bearing with me on that one. Had to get a little Halloween out of my system. Hopefully you enjoyed or were not too frightened by seeing the bottom half of my face when normally it's the top half that is exposed. At any rate, let's look at this problem. Pumpkin drop. I want to point out that once again, we are studying falling objects, right? And we can calculate their potential energy and their kinetic energy, knowing gravity, and we can even find their velocity. So, to make it thematic, it's a pumpkin drop. So let's look at the problem here. Oh, don't forget to put your name on the paper. So, you're going to download this from Teams, of course, and work on this as we go through it together. So Halloween is over, and Jacinda and Kyle decide to put on a show for the kids in the neighborhood by dropping their jack-o'-lantern from the roof. Their dad helps them bring the 1.5 kilogram pumpkin up to the 12-meter roof, and as the little kids cheer them on, they let it fall to the driveway below. So here's everything you need to know is in there, combined with the equations that we will be working with. We already probably have memorized, I hope you've memorized this one, mechanical energy equals potential energy plus kinetic energy. You don't have to memorize any of the other ones, but you need to know how to use them. Potential energy equals mass times gravity times height. Kinetic energy equals 1/2 the mass times the velocity squared. Gravity, you might remember, is 9.8 meters per second squared on Earth. I don't know about on the gravity where that guy came from. And then if we take this equation of kinetic energy equals 1/2 mv squared, and we rearrange it using algebra, we can isolate the v of velocity to find that velocity is the square root of 2 times the kinetic energy divided by the mass. So we'll be using all of these equations here and there. Now your instructions are inside this box. So first one, draw an energy diagram. Remember, that'll be a rectangle showing the amount of energy. So draw an energy diagram next to the 3 locations of the ball as it falls to the ground. The ball, that's not a ball, it's a pumpkin. I'm going to change that before I post it. At any rate, here's the 3 locations. The 12-meter rooftop, 50% of the way down at 6 meters, and then it hits the ground, hits the driveway at 0. You need to make 3 separate energy diagrams to show these. I just want to remind you that an energy diagram is basically a rectangle, and you choose some color to fill it with. I did that by hitting properties. Oh, I should really go with orange since this is Halloween themed. So there's my first energy diagram. And to change its color, I just right click, then I click on properties, and I can change the color of the center of it or the edge of it, the border of it. Now, I need to show 3 energy diagrams. That one seems a little tall to me. I'm going to shorten it up a little bit. There's my first energy diagram. And you might remember that at the starting point, it's all what kind of energy? Well, we're studying both potential and kinetic. What I would like you to do here is label how many percent potential energy we have here and how many percent, and I'm going to let you figure this out for yourself, kinetic energy we have here. You can see it's a hint. It's all of one and none of the other before it falls, right? Then I'm going to take this, and the easiest way for me is to copy it and paste it. Now I know it's exactly the same size. I want to remind you, it's the same size because the total energy remains unchanged. Even if we convert one kind of energy to another, the total energy remains unchanged. I'm also going to copy and paste this. Oh, that was interesting. I got 2 for 1. And this is going to be my third energy diagram down here at the ground. When this jack-o'-lantern hits the ground, then this guy is going to be here. I'm going to copy and paste that also. One more time. Sometimes you got to click multiple times to get what you want to be activated. I think I'll just do it this way. It seems like that's going to be the most cooperative. And then I'm going to start a new text box down here. Control V will paste it for me. If you have a Mac, it's Command V. So Control C to copy, Control V to paste, or Mac's Command C and Command V. Now, halfway down, how much of this should be potential and kinetic? I will tell you now this is no longer correct. I want you to fix that for yourself, and I want you to label these percentages. When it's at the exact halfway point, 6 meters down from the 12-meter drop, if it's halfway, that should give you a pretty good hint of how much should be potential and kinetic, right? Similarly, when it hits the ground, the very moment it hits the ground, how much of it is potential and kinetic? You will need to change this box to match what's going on. So this is the physics of the fall. So let's see. I made 3 separate energy diagrams. They show the total amount of energy, and they also show that the total amount of energy did not change because of the law of conservation of energy. We can't create it or destroy it, so the total energy remains the same size. Your energy diagram should show the amount of each type of energy at each location. So this one is okay to start with as long as I label these correctly. But these other two need to be changed to show those energy conversions. Finally, I need to make a key that explains the diagrams. So I'm going to grab this again, Control C, copy, Control V, paste. I'm going to make it a nice little square here. And I'm going to label that as, let's see, it's my potential pumpkin energy. Then I'm going to copy and paste this. But I need a different color to represent my kinetic energy. So I right-click, go to Properties. I'm going to fill it with black to stay with my Halloween theme here. Oh, I think I'll make the edges be orange still, so it'll look kind of Halloween-y. And then this is going to be kinetic energy. Okay, so there's the key. There's the beginnings of the energy diagrams, but you have to fill in the blank percentages, and you have to modify these 2 energy diagrams at the bottom to be correct. So please pause the video until you've finished those things, and then come back. And we'll pick it up where you left off. Okay, yeah. Ready to move on to the next part. Let's go back here. All right, so down here, we're going to do a bunch of math. Use the info above to complete these calculations, all these calculations down here. Show how you set up the problem for partial work. In other words, show how you set up the problem for partial credit. In other words, show your work. You can see we have 3 sets of problems to calculate. Before the pumpkin is dropped, we're going to find PE, KE, ME, and velocity. Halfway to the ground, we'll find those 4 things again. And then the moment of impact, we will find those 4 things again. How are we going to do this? Well, we need to use a calculator, so get one ready. And we need to use these equations, So to start with, we find PE at the top. PE equals mgh. So that's the equation we're going to use here. PE equals mgh. So that means I need to take the mass of the pumpkin. What was that? Here it is in the opening. 1.5 kilograms. 1.5. I have to multiply that by gravity, which I remember is 9.8. And I have to multiply that by the height from where it fell. It was a 12-meter roof. Okay? So that is how you show your work. You write down the equation you're going to use, and then you show the numbers that you're going to fill it in with. Then you do the math on your calculator. Once again, I'm going to let you do that by yourself. So take a moment to do that. Pause the video. The video is going to move right on to KE, but I think you can pause it and finish PE first would be a good idea. So KE, well, that equals 1/2 mv squared. And I like to make my second number for the squaring in a separate box and then move it up here. So it looks like that. But since the pumpkin has not moved yet, we're holding it steady at the top of the roof. We're ready to drop it. That means that it's not moving. So kinetic energy is simply going to be 0. 0 joules, right? We want to label our measurements. 0J. Okay, that one should be simple. Mechanical energy, this is the one I want you to memorize, but let's just review. All you have to do to find mechanical is add potential and kinetic together. And that means, let's see, ME equals PE plus KE to show my work equals, what was it? Oh, whatever you got up here, whatever number you got here for potential energy, you add that to the kinetic energy of 0. And don't you get the same answer up here? Whatever you had up here, when you add 0 to it, you get the same thing down here for ME, right? So I'm going to let you do that on your own. The last thing is the velocity. How fast is this pumpkin falling? Well, wait a minute. We haven't dropped it yet. We don't even need to do math for this first position, do we? And if we did, because KE is 0, if we plugged it into this equation, 2 times 0 is still 0, divided by the mass is still 0, and the square root of that is still 0. So it makes total sense that before we drop it, it's not moving. Therefore, it's going to be 0 meters per second. That's how fast it's falling. It's not falling, just sitting there. Okay? Now, I'm going to make up a number here, just so you can see what's going on. 1.5 times 9.8 times 12. You should have an answer that's around, let me see. I'm thinking your answer should be close to 120 times 1.5. Your answer should be somewhere between 100 and 200 is my estimate. And you might want to do that too to see if your answers are making sense. I just took 12 times 10, which is 120, and 1.5 of that, let's see. A half of 120 is 60, so if I add that to the 120, I get 180. Your answer should be pretty darn close to 180, whatever it is. So this isn't the answer, but it's close to this answer, 180J, which means here I would have had 180 plus 0 equals still 180 joules, right? Now, the nice thing is because of the law of conservation of energy, we know that whatever we have here, it stays the same halfway to the ground and at the ground, it's still 180 joules because of the law of conservation of energy, right? Now let's think about this. Again, this is not the exact answer, but it's close to it. I want you to give me the exact answer, okay? Now, if I recall, ME equals PE plus KE. There it is. Which means this 180 is these two things combined. And if it's halfway to the ground, that means I take the 180 divided by 2, and I will get 90. You won't get exactly 90, but you should be close to that. So PE, in this case, I approached it a different way. I should also get the same answer if I did 1.5 times 9.8 times 6. I should get the same answer here. So there's two ways to get it. I find this the easiest way, but I could check my work. 1.5 times 9.8 times 6 should be the same answer. Let's see. If I did 10 times 6, that's 60. 1.5 of that, let's see, half of 60 is 30, plus the 60 I started with makes 90. Oh, look at that. It is the same for my estimated answer. For you, it's not exactly the same. Give me the actual answer. And here, we do the same thing. 180 divided by 2 equals, once again, 90J. And if we did it right, 90 plus 90 equals 180. Yeah, mechanical energy is these two things combined. Okay, now we get to velocity. And this is a little trickier. To find velocity, we have to use this equation, but we have to rearrange it to isolate v. We have to get v by itself. Let's see how I did that. First, I multiplied by 2 to get rid of the 1/2. But if I multiply this side by 2, I have to do that also. So I end up with 2ke. See that right there? 2ke. Then to get the v by itself, I have to divide by m. So I get 2ke over m. But wait a minute, that would give me v squared. So to find v squared, I have to take the square root of, to find v by itself, I have to take the square root of v squared. But if I take the square root of this side, I have to take the square root of this side also, which gives me v equals the square root of 2ke over m. All right, so let's see how we're going to do that. It was square root, which is a little trickier to do. Let's just say root, since we don't have a square root sign, the root of 2ke over m. That's the equation we're using, right? So how am I going to do that? I'm going to go from the inside out. Start with 2ke. So 2 times 90 is where I begin. I divide that by m. What was the mass of this pumpkin? Was it 1.5? Yeah, 1.5, 1.5. I divide that by m. Oops. Once I've done that, then I use the square root function on my calculator. If you're using your phone like I am, then you'll need to turn the calculator sideways. Or maybe I have a calculator here. Let's see. Yes, I do. Does it have a square root function? Standard, okay. I can go to a scientific calculator. That's what I want. Now I have a square root function. Sometimes they put a little 2 in there to show it's the square root, because you can also do cubed roots and fifth roots and crazy stuff, but we don't need to worry about that. So what did I say we're going to do? We're going to go 2 times 90, then hit the equals button. I'm going to divide that by 1.5. Hit the equals button, 120. Then I hit the square root sign, and it went straight to it. There's my answer, 10.9545, etc. I'm just going to round this up off to 10.95. 10.95 meters per second. Now your answer is not exactly the same as this, but it should be close to this. It should be close to 10. Okay. So if you need to pause the video, now is a good time while I move on to the next section. At the moment of impact, just when the pumpkin hits the ground. Let's see. Oh, as I recall, of course, ME is the same every time, 180 joules, huh? And as I recall, at the moment it hits the ground, well, it can't fall any further than that, so PE has got to be 0. We know it's already on the ground. There is no more potential energy left. It does not have the potential to fall further. Now, if ME was 180 and potential was 0, that means all of the energy had to be kinetic, so it should equal the mechanical. So KE equals 180J. Oops, 180J. Yeah. Hopefully that makes sense to you. Let's double check. 0 plus 180 makes 180. 90 plus 90 makes 180. 180 plus 0 makes 180. We just kind of flip this thing around, huh? Now, what is the velocity when it hits the ground? Once again, we're going to use this equation, the square root of 2ke divided by m. Okay, the ke is different now, isn't it? So it hits at a different velocity, and it should make sense. It should hit at a faster velocity because it's fallen further. So it has more kinetic energy when it collides with the ground. So let's go back to the calculator. Let's make sure everything's clear. Okay, it looks clear. What do I have to do? I have to go 2 times ke, not 2 times 90, but 2 times 180. That's why it's going to hit faster, isn't it? And then I got to hit the equal sign before I divide by the mass, which was 1.5. I hit the equal sign again. I get 240. Now I take the square root of that. Whoops, that's x squared. Make sure it's the square root. 15.491. Okay, so my velocity equals 15.49 meters per second. See, it sped up as it fell further through the air, and it hit the ground at a higher velocity than when it started. So we finished that first page. Pause the video to do the math for yourself. Your answers are not the same as these, but they should be close to these. Well, some of them are the same. The zeros should all be the same. But your exact answer won't quite be the same as mine. It should be pretty darn close because I just rounded this off to 10. Okay. Come on back when you're ready. I'm going to move on to page 2. Surprise! The pumpkin was actually made of rubber and it bounced back up 8 meters. The little kids were mad that they got tricked instead of treated. Jacinda and Kyle, tricksters. At any rate, on the right side of the graph, here's the graph. Draw the pumpkin at the moment it bounces upward from the ground. So we're going to take a pencil and let's see, I'm going to make a circle. That'll be much easier. It's not a perfect circle, but Oh, I can kind of do this. I bet I can warp it a little bit. How about that? There's my pumpkin. Be nice if I could stretch it. Oh, look at that. Especially if it's rubber, doesn't it stretch out a little bit at impact? Right? That would be due to what kind of energy? Think about it. On the right side of the graph, draw the pumpkin at the moment it bounces upward from the ground. Check, I've done that. Next, draw the jack-o'-lantern at the maximum height of its bounce. So I should probably include an arrow showing that it's bouncing upward, right? And how high did it bounce? 8 meters. Wow, that is one bouncy jack-o'-lantern. So I'm going to take this, I'm going to copy and paste it. I'm going to put the bottom of it at 8 meters, because remember, we were considering the bottom as our measurement point. I'm going to make it a nice circle now because it's bounced back, right? So I need to make that measurement precisely. When I look at your paper, I should see that you actually graphed it in the correct location. So now I have taken care of the first 2 bullets. I've drawn the pumpkin when it hit the ground, and I showed an arrow that it's bouncing upwards, and I drew it at the height of its maximum bounce. So if you need a minute to do that, pause the video. I'm going to move on. Let's see. I'm going to draw energy diagrams next to the 2 locations of the pumpkin, here at the ground and here at the bounce. Now I know that it has the same energy at the beginning of the bounce that it had at the end of the bounce. So I'm going to copy this energy diagram from the beginning of the bounce, and I'm going to paste it over here. Where did that go? There it is. I knew I pasted it. Sometimes it pastes it off your screen where you can't see it. So here it is at the beginning of the bounce. Now we need to think a little bit. What kind of energy was lost when it hit the ground and bounced? And I have to show those losses. So I'm going to zoom in here because I'm going to have to make some pretty small boxes to show those energy losses. So let's see. I'm going to have first a box. Let's see. I need to make it the right width, huh? Do you guys remember those 3 kinds of energy losses we talked about? I need to change its color. I'm going to make this one be green. I'll make that a little bit bigger. Maybe it'll help if I make the borders green too. It'll show up a little better when I zoom back out again. Borders green. So there were 3 types of energy that were lost when it hit the ground. There's one of them. I'm going to copy and paste that now. I'm going to line it up here. And they're probably not actually equal to one another. The amounts of energy that are lost are not equal to each other of these 3 different kinds. But we haven't been given any information about how much energy was used. I'm going to make this one be this kind of purplish color, both the inside of it and the border of it. So there's my second kind of energy that was lost. I'm going to paste that bar again, and really these would not be exactly the same size. It'd be awesome to make them correct, but we're not going to worry about it. I'm going to make this one be blue. Just to emphasize that these are actually different kinds of energy and different amounts of energy coming off of them, I'm going to make that one slightly different sized. So we lost this energy, right? So I'm going to show a little arrow. Shows that this energy was lost. I think I'm going to try to draw a little bracket. Oh, I'm surprised I did it that well. I do think that's a little too fat of a line, so I'm going to change this to 1 point. Yeah. And I'm going to label this as energy lost. I'm going to move this over here so it stays on that side of the line. I rearrange my arrow as needed. This energy was lost, right? This energy was still present. And at the beginning of the bounce, it's starting to move. So wait a minute, this isn't potential energy, it's on the ground. There is no potential energy, is there? So that must mean that this is all kinetic energy. So I'm going to take this bar, pasted it on there, and I'm going to cover up this orange bar. The nice thing about using this orange one was that I made sure it was the same size as before. And I think I used kinetic energy was black, right? I think it was black with an orange border. So this is starting to move. That's now kinetic energy going upwards. Okay? All this energy, the blue, the purple, and the green, and I'm still asking you to think about what are those three kinds of energy that are lost when an object hits the ground like that. We'll come back to that in a minute, so keep thinking about it. So that's all lost. And this kinetic energy is left behind, and that's what the pumpkin, in this case, carries upward with it. Only this energy. So I'm going to copy and paste this box. I know it's the right size for the amount of energy I want to represent. All I have to do is think about what kind of energy is this? Well, wait a minute. It's at about the same height as that. Does that mean it's 50-50? Half potential and half kinetic? Well, it would be, except wait, two things. Number one, it's not at the halfway point. It's actually higher than that. But really, we need to think about this very carefully. Right now, the ball at the top of its bounce, the maximum height of its bounce, it pauses for a minute. The pumpkin falls down. It bounces back up. I know I just called it a ball. It's a pumpkin. It falls down. It bounces back up. And at the highest point, it starts to fall again, huh? Isn't there a tiny fraction of a millisecond when this is moving upward, the motion pauses, and then it falls downward again? We're measuring it at the pause, so it's not moving at all. So I have to ask you, does it have any kinetic energy at the top of the bounce? Does it have potential energy at the top of the bounce? Well, wait a minute. It's off the ground, so yes, it must have potential energy. The question becomes, what percent is potential and what percent is kinetic when it's at the top of its bounce again? It has paused in midair. So I would like you, once again, I'm going to take this, Control C to copy, Control V, whoops. Control Z or Command Z is a good way to undo something. So I'm going to go over here and I'm going to copy this back here. I'm going to click text. I'm going to click to start a new text box, and I'm going to paste this in there. I would like you to label this and color this correctly. I'm not going to do this one for you, but I'm going to give you these hints that the ball has stopped moving and it's ready to fall. It's almost like we're just dropping it all over again. So let's see. We drew the jack-o'-lantern at the maximum height of its bounce. We drew the energy diagrams. Yeah. Your energy diagram should show the total amount of energy at each location. That's the total size of the box, regardless of how many energy bars are inside of it. So this matched the box from page 1. I like that. I've shown that it kept that same total energy when it bounced. But at that moment, some of that energy was lost. We were only left with this much kinetic energy. It bounced upward. Might be nice to show that. And when it reached the top of its bounce, how much is potential, how much is kinetic? I have to show the amount of each type of energy. Yeah, I think I've done that, except for this one that I want you to think about. Next, we need to make a key. I'm going to command and paste this guy. I'm going to have that be on my key. How many colors do I have to put on my key now? I need that. Command to paste that. I'm going to turn it to orange just in case I need that potential energy too. These diagrams should match from page 1 to page 2, right? So here's my KE. Here's my PE. Then I am going to paste that again and again and again. Why did I do it 3 times? Well, didn't I have 3 other types of energy at the moment it hit the ground down here? One of them was blue. One of them was, what is that? Purple? And one of them was green. Who's that green? Lime green? Tennis ball green? What are those 3 types of energy that were lost? Well, let's think about it. It hits the ground and it squashes. It changes shape and then bounces back, changes shape again. Do you remember what that was? When something can be stretched out and then bounces back to its original shape again? That's one of them. Think about that. What are you going to label that one? And it doesn't matter which of these 3 it is. What else happens when it hits the ground? Oh, I remember. We can hear it hit the ground, right? Boing, in the case of a rubber ball. So if we're hearing something, doesn't that take energy? And that's lost from the energy of the fall during the collision. So one of these should be labeled that type of energy. The third one is a very subtle one. When it hits the ground, the friction from the collision of the jack-o'-lantern in the ground or the ball in the ground or whatever, that friction creates a tiny amount of heat. So what do we call that type of energy? All right. So I want you to think about that for a minute. If you need to pause and discuss with your neighbors, what would those 3 kinds be? Go right ahead and do that. Ideally, you don't just give one another your answers. You help them think about it. Like I didn't give you the answers, but I gave you some pretty good hints. That's how you help somebody. That's how you work together. Instead of just give them the answer, oh, 3. You help them figure out how to get that answer of 3. Otherwise, they're not going to be able to do it on their own. So if you really want to help your friends, don't just give them the answers. Give them the tools to figure out the answers for themselves next time. Help them learn how to do this. That's how you actually work together. It's the difference between working together and copying. All right, enough of that. Pause as needed. I'm going to move on to these questions. Did this pumpkin itself lose energy, gain energy, or keep the same amount of energy during this bounce? Did the pumpkin lose energy? Did the pumpkin gain energy, or did it keep the same amount? Well, think about it. What's the law say? Oh, energy cannot be created or destroyed, but it can be transferred and converted. So I think we had both a transfer of energy when energy went out of the pumpkin and into the air or into the ground. We had a transfer of energy. We also had conversions of energy where the original energy type potential was converted into kinetic, and then that was converted into these 3 different kinds. So we had both transfers and conversions of energy. So what do you think? Did it lose energy? Did it gain energy? Did it keep the same amount? Remember, our energy diagrams should show how much energy the pumpkin has. So originally, the pumpkin had this much energy. It still had that same amount of energy as it fell, still had that same amount of energy as it collided with the ground. Then some of that energy was transferred away and converted into different types. and the pumpkin now on the bounce back only has this much energy. Was that energy destroyed? Or was it just lost to the environment? Number 5, did the universe lose, gain, or keep the same amount of energy during the bounce? If the universe lost energy, that would mean energy was destroyed. If the universe gained energy, that means energy was created. If it kept the same amount of energy, that means energy was conserved. What do you think? Those two take us right into number 6. Name and describe the 3 parts of the law that you use to answer questions 4 and 5. Name the law, describe the 3 parts of it. We've practiced that. You should know how to do that. Pause the video as needed, of course, as you're answering these questions. I'm going to move on just to save recording time. Number 7. Describe any changes in energy that occurred during the bounce. Well, I think I actually just talked about that. During the bounce, when the pumpkin hits the ground, it's all kinetic, right? I didn't color it correctly here because I wanted you to think about it. But it is all kinetic when it collides with the ground. Then some of that energy is converted into these 3 different kinds. And then it's transferred out of the pumpkin, mostly into the air, but also a little bit of it into the ground or into the driveway in this case. So describe these changes in energy. It would be awesome if you used both a description of the transfers of energy from one object to another, from the pumpkin to the air. It would also be awesome if you used descriptions of conversions of energy where it gets changed from one kind of energy into another. So there's 2 ways to think about those changes, transfers and conversions. Can you discuss both of those in that question? I'm going to move on to number 8. You pause as needed. Let's see, I'm going to zoom out a little bit. Number 8, calculate, we get to do math again, calculate the energy in the pumpkin at the top of its bounce when it paused before falling again. So the top of its bounce, that's this one. How much energy is there? Let's see. Hint, if it's up in the air but not moving, it paused before falling again, it must only have PE. Oh, wait a minute. How do I calculate PE? That's right. I use this equation. PE equals mass times gravity times height. So that's what I'm going to do here. And you know I like it if you show your work. For one thing, it makes me think that you're doing the work yourself instead of just copying the answer from a neighbor who figured it out. You need to be able to do this for yourself too, huh? What was the mass of the pumpkin? As I recall, it was 1.5. Mass 1.5 times g, gravity. I've memorized that as 9.8. If you haven't memorized it, that's okay. You just look at the chart with the equations and it will be there for you. H, how high did it bounce? 8 meters. Let me double check. Did I draw that? Yeah, I drew that at 8 meters, huh? So 1.5 times 9 times 8 equals our new potential energy. Plug those numbers into your calculator and math them out. Let me see. I'm going to estimate this as 10 times 8 is 80. 1.5 of that. Let's see. Half of 80 is 40. Plus the original 80. You should get close to 120 joules. Close to 120 joules. Not exactly. All right, that takes care of number 8. If you need time, pause the video. Number 9, calculate the amount of energy that was transferred out of the ball during the bounce. Well, wait a minute. Nobody gave me any equations to figure out these 3 kinds of energy. Oh, but wait a minute. I know that it had this much energy to begin with. It was about 180 joules, wasn't it? Right? That's how much energy it had to start with. when it hit the ground. When it bounced back up, this much was lost. This much stayed with the ball, which I just calculated as 120. So the amount of energy transferred out must just be subtraction. It's the original, oh, nice spelling, huh? The original, there, nope, I was right the first time. Original energy minus the new energy would be 180 joules minus 120. I can do that in my head. That's 60 joules is the amount of energy that was transferred out. Now, I haven't separated those into the three different kinds of energy that were transferred out. It might be 20-20-20, it might be 30-20-10, or some other combination of these three different kinds of energy. In the future, we're going to try to figure out those things separately, or maybe they'll be given to you. But what I do know is if I started up here with 180 joules, it still has 180 when it's halfway down. It still has 180 when it hits the ground, but then when it hits the ground, some of this energy was lost and it bounced back up. And I can tell by how high it went that there's 120 left. If there's 120 left, that means that this loss had to be 60 joules with these three things combined. Now, your answer should not be exactly 60, but it should be pretty close to it. Go ahead and do your math, pause the video if needed. I'm going to move on to number 10. So we're going to calculate the efficiency of the bounce as a percentage of the ball's original energy, and I've given you this new equation for efficiency. Think about that. Some balls have a more efficient bounce than others. It's impossible, but if a ball was able to bounce all the way back to its beginning point, it would have an efficiency of 100%, wouldn't it? If it bounced all the way back to the same starting point, it would have an efficiency of 100%. That is impossible in our universe, but if it did, I hope that makes sense to you. On the other hand, if the ball bounced exactly halfway back to where it started from, wouldn't that be an efficiency of 50%? Oh, and that makes me think of something. I can estimate what my efficiency should be here. Where did I drop it from? 12. It bounced back to 8. That means my answer better be more than 50%, huh? If it bounced only to 6, that would be halfway from where it started from, and its efficiency would be 50%. It bounced more than that, so this ball is more efficient than 50%. So we can calculate that efficiency. How much of the energy is retained when the ball bounces? How efficient is it? The more efficient, the less energy is lost. The more of it keeps going. So you take your ending energy, divide by your starting energy, multiply that by 100. So for me, that would be 120. That's what I ended with. And a divide by 180. What does that make? Let's look at the calculator again. 120 divided by 180. Hit the equal sign. 0.666 forever. I have to multiply that by 100 to change it to a percentage. So my answer is 66.67%. Oops, I'm supposed to do that here. 66.67%. Your answer should be pretty close to that, but it won't be exactly that. All right. Or maybe it will be exactly that. It just might be closer than I thought. At any rate, that finishes this worksheet. So what I'd like you to do is turn it in, of course, put your name in the file name, of course, upload it to OneDrive, of course, add it to the table of contents, of course. And then I would like you to go back to wherever we left off on the big project and see how much further forward you can move on that big project. The other thing I'd like you to keep in mind was my spirit's little advice at the beginning that this page is going to really help a lot when it comes to the exam. I think you will find that the exam looks amazingly similar to this page. If you can do this math now, if you know how to convert the story problem into math problems now, you're going to be well ready for the exam. In fact, the night before the exam, I would advise you to complete this worksheet again. It's basically your study guide for the exam. Okay? And if you get lost, well, you've got this video to help you figure out where you left off. Okay, just something you should know. This is going to help when it comes to test time. All right. Yeah. Okay. Well, it's nice to see you guys even though I'm absent today. And don't forget to study for the exam. There we go. And have a good day.